Hello, good morning. Is my screen frozen? Oh, my screen is frozen. Hello. OBS lagged. OBS, something happened with OBS capture. Okay, I think it's good now.
So let's define a random variable x as being equal to the number of heads. I'll just write capital H for short. The number of heads from flipping a fair coin. We're going to assume it's a fair coin. From flipping coin 5 times. 5 times. And so like all random variables, this is taking particular outcomes and converting them into numbers. And this random variable, it could take on the value x equals 0, 1, 2, 3, 4, or 5. And what I want to do is...
Hey, hello. How are you, King? Good morning. It's 5 a.m. here, 5:41. Yeah, we are doing statistics today. So, hope you enjoy the stream. I'll get some water first. Ah, 4:41 a.m. I'm doing well. I just woke up. Oh, I see. It's like 1 hour difference. Where do you live? A 1 hour difference? Do you live in Myanmar? No, not in Myanmar. Myanmar is 30 minutes difference. 30 minutes. Singapore? Bangladesh. Oh, I see. Is there too many PM 2.5? I heard like Bangladesh. How do you spell out Bangladesh? Fuck Myanmar. Is that too? Yeah. Yeah. The air quality is pretty bad. How about Thailand? Yeah, it's alright. Whoa. Terrible up here. Kabul? Where's Kabul? Iran. Dang. Really? Oh. Yep. How about the European country? European country are all green. Canada? It's red. Oh, I see. Like the wildfires, huh? Russia. It's wildfire again. Yeah.
Just figure out, well, what's the probability that this random variable takes on 0, can be 1, can be 2, can be 3, can be 4, can be 5. And so to do that, first let's think about how many possible outcomes are there from flipping a fair coin 5 times. So let's think about this. So let's write possible outcomes. Possible outcomes from 5 flips. From 5 flips. These aren't the possible outcomes For the random variable, this is literally the number of possible outcomes for flipping a coin 5 times. For example, one possible outcome could be tails, heads, tails, heads, tails. Another possible outcome could be heads, 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 tails, tails. That is one of the equally likely outcomes. That's another one of the equally likely outcomes. How many of these are there? Well, for each flip, you have two possibilities. So let's write this down. So so the first flip.
Oh, impossible. You the country. Oh, by the way, I'm not gonna tell you that you guys miss out on something, but if you check my stream correctly, you miss out on something. So I'll let you figure out what did you miss out. I give you this. It's involved with Twitch. All right. So figure it out. Empty Goshi bags and King. Figure it out. You guys missed something.
There's two possibilities.
No. Oh, close. Close, King, close. We miss out on the Fury Pawn. You ladybug makeup. No. It involves with Twitch. I give you that. Yeah, I'm affiliated right now. Close, empty ghost bag, close. Figure it out.
Times 2 for the second flip, times 2 for the third flip. Actually, not use the time notation. We might get confused with the random variable. Two possibilities for the first flip, 2 possibilities for the second flip, 2 possibilities for the third flip, 2 possibilities for the fourth flip, and then 2 possibilities for the fifth flip. Or 2 to the 5th equally likely possibilities from flipping a coin 5 times, which of course is equal to 32. And so this is going to be helpful because for each of the values that the random variable can take on, we just have to think about, well, how many of these equally likely possibilities would result in the random variable taking on that value? And let's just delve into it to see what we're actually talking about. All right, and I'll do it in I'll start in blue.
Just say it, ladybug. Okay, I give you another hint. It involves in chat, Twitch chat. All right. It's nothing for me. It's for you guys. All right. It's involved in Twitch chat. Wait, let me see if I have. Yeah, channel points. I don't see anything. What? Wait. Here. Okay. Yeah. And then there's third. Okay. Someone redeem? You guys redeem already? Who redeemed the first? What? Someone redeemed the first? You Where's the first? Right. Where's the first? Yeah. A zebra. Okay. Where's the first? Who did the first? What? Alright, there's a third possible outcome. A third possible, but never mind. Every time enjoy. Okay. I guess it's buggy.
All right. So let's think about the probability that our random variable x is...
Can I ask mod? Can I ask mod? What? What do you mean, can I ask mod? Can you become mod? That's what you're asking?
Equal to 1. Well, actually, let me start with 0.
No.
Probability that a random variable x...
Can I hash mod? Yes. What do you mean, can I hash mod? Do you mean, can I become mod? The answer is no. I don't trust you. I trust empty grocery bag. I trust Swagger. But I don't trust you. I don't know you.
Is equal to 0. So that would mean that you got no heads out of the 5 flips. Well, there's only one way, one out of the 32 equally likely possibilities that you get no heads. That's the one where you just get 5, where you get 5 tails. So this is just going to be, equal to 1 out of the 32 equally likely possibilities. Now, for this case,
mod who? Or empty grocery bag? He didn't ask for it.
You know, to kind of think in terms of kind of the you know, binomial coefficients and combinatorics and all of that, it's much easier to just reason through it. But just so we can think in those terms, and it'll be more useful as we go into higher values for our random variable. And it's also, you know, this is
possible outcome of 5 flips. Okay.
It's all a build up for the binomial distribution, so you get a sense of where the name comes from. Let's write it in those terms. So this one right over here. One way to think about that in combinatorics is that you had 5 flips and you're choosing 0 of them to be heads. 5 flips and you're choosing 0 of them to be heads. And let's verify that 5 choose 0 is indeed 1. So 5 choose 0, let me write it right over here. 5 choose 0 is equal to 5 factorial over 5 minus 0 factorial over 0 factorial times 5 minus 0 factorial. 5 minus 0 factorial.
Wait,
well, this is 0 factorial.
Combination, right?
Is
yeah, that's combination. Combination, yeah.
1 by definition, and so this is going to be 5 factorial over 5 factorial, which is going to be equal to 1. Once again, I like reasoning through it instead of blindly applying a formula, but I just wanted to show you that these two ideas are consistent. So let's keep going, and I'm going to do x equals 1 all the way up to x equals 5, and if you are inspired, and I encourage you to be inspired, I try to fill out the whole thing. What's the probability that x equals 1, 2, 3, 4, or 5? So let's go to the probability that x equals 1. So the probability that x equals 1 is going to be equal to, well, how do you get 1? The second one could be head, and then have that one head. 5, which of course is the same thing. This is going to be equal to 5 out of the one of them. And you could verify that 5 factorial over it, just so that you don't have to take 5 times going to be equal in is equal to the combinatoric.
5 choose 2 is what? Why do you still have the prediction? Hell no. Prediction outcome. Wait, the prediction is still there. Oh, choose outcome. I see. Hell no. Wait. Oh, I see. So yeah, I did not make red black tree. Yep. Okay. Alright, so prediction is over. Cool. Striker created, but he didn't answer it.
So this
He
is,
didn't choose the answer.
you have 5 flips, and you're choosing
Bad
2
mod.
of them to be
Bad.
heads over 32 equally likely possibilities. So this is the number of possibilities that result in two heads. 2 of the 5 flips have chosen to be heads. I guess you could think of it that way, by the random gods, or whatever you want to say. And so this is the fraction of the 32 equally likely possibilities. So there's a probability that x equals 2.
Okay, if I choose 2 is 5 factorial. 2 factorial times 5 minus 2 factorial 10, right?
2 minus 4 times, and this is even, everything is in x equals
10. Is this binomial distribution? Is that it?
Probably have 5. So we have 5, since I've done it, it would be 1. The probability of getting 5 heads is the same as the probability of getting 0 tails. And we represent this. And we'll see the problem.
So, yeah. Okay. Okay, we can use Excel for this. Excel. Where is it? No. So you can use binomial stats, okay, and then false accumulated, right? Don't save. Okay, so you can use this, and if you want to find, you can minus that. Cool. Normal distribution. Okay.
Hey guys, it's Mark from Ace Tutors, and in this video, I'm going to explain one of the most common probability distributions covered in STAT, the normal distribution. First, I'll go over this concept at a high level, then I'll explain how this distribution is used to find probabilities, and finally we'll finish things off with an example. And just quickly before I begin, if you would, please consider tapping those subscribe and like buttons below to help us keep making videos like this for students like you. So now let's dive right in. First of all, a normal distribution looks like this symmetric bell-looking thing, which is why it's often called a bell curve. Now this curve is centered around the distribution's mean and spreads out with decreasing probability as you move away in either direction. Although the normal distribution technically continues indefinitely in either direction, it only really has significant probability values between 3 standard deviations below and above the mean. In fact, as a general rule of thumb for a normal distribution, between plus or minus 1 standard deviation, there is 68% of the distribution's data. Between plus or minus 2 standard deviations, there is 95% of the data. And finally, between plus or minus 3 standard deviations, there's 99.7% of the data. Now, the reason I called this distribution one of the most popular ones is because it can be used for so many types of real-world applications. For example, certain things like people's heights, weights, and even IQ follow a normal distribution pretty closely. However, because the normal distribution is so widely applicable, and each application comes with its own mean, standard deviation, and most importantly, units, this causes some problems. To solve this issue, instead of keeping the data in its original units, we get rid of the units by doing what's called standardizing the data. Essentially, we take our original distribution and transfer it to have a mean of 0 and standard deviation of 1. As a result, any normal distribution of any magnitude or unit type can be converted to be centered around 0 and extend more or less from -3 to +3. Okay, that's cool, but how do we actually do that? Well, in order to standardize the data, we need something you may have already heard about in your class, the infamous z-score, which has a formula of z equals the data point x minus the mean mu divided by the standard deviation sigma. Essentially what the z-score tells you is how many standard deviations a certain data point is away from the mean. So for example, if the heights of people in your stat class were normally distributed with a mean of 66 inches and standard deviation of 2 inches, your unstandardized distribution would look like this, centered at 66 inches and spreading out by increments of the standard deviation like this. If you happen to have a height of 67 inches, you would fall right here in the distribution, slightly above the mean. If we were to standardize your data point, we would find that your z-score equals 67 minus 66 divided by 2, which is 1/2 or 0.5. This z-score of 0.5 means that your data point is half of a standard deviation above the mean, and located here, the same exact location in the distribution as before. Alright, now that we covered how and why we standardize normal distributions, let's move on to the most important part of all probability distributions, and that's, well, probability. Now, unlike the other distributions we covered, there isn't a nice and pretty formula for figuring out probabilities for the normal distribution. Instead, to calculate probabilities for this distribution, we have to rely on using charts, which might look like these, where numbers on the leftmost column and topmost row correspond to your z-score, and the interior numbers correspond to those z-scores associated probability values. So for example, if your z-score was 0.63, you'd go down to the 0.6 row, corresponding to the 6 in the z-score's 10th place, and over to the 0.03 column, corresponding to the 3 in the z-score's 100th place, to get the associated probability value of 0.7357. Okay, but what does that value actually mean? Well, in order to know that, it's very important to understand what values the z-chart you're looking at gives you. For these z-charts, it happens to give you the area or probability of being to the left of your z-score. So for our previous example, based on the value found in the chart, there's a 73.57% chance of having a z-score less than 0.63. And one last quick note, it's also important to make sure you are using the correct chart based on whether you have a negative or positive z-score. The one on the left is for negative z-scores or values below the mean, and the one on the right is for positive z-scores or values above the mean. Alright, I know I've been throwing a ton of info at you, so let's solidify all of this with a quick example. So you love pizza, but your local pizza shop's pizzas have been looking smaller and smaller lately. They claim that their large is at least 16 inches or it's free. Over your expansive pizza eating career, you've found that their pizzas are normally distributed in size with a mean of 16.3 inches and standard deviation of 0.2 inches. Now you want to know what the probability is of getting a free pizza. Also, what's the probability of getting lucky with a pizza that's over 16.5 inches? And just because you love stat and love eating pizza, what's the probability of getting a pizza that's between
Good morning. Oh, ต้นข่าว click this and then select this one. I think you become third. Try this one. Do you have bits channel points? I see. So you select it now and then this is Strager's application, I said, and then you become in the leaderboard. See, you're third now. So every time if I stream and you're lucky, you can click the first button. There's first. So the first is out already, right? But whenever I start a new stream, you can click first and you have more points, and you can, become first in the leaderboard. So there's Strager. So see, yeah.
15.95 inches and 16.63 inches. Okay, first, let's draw our normal distribution centered at the mean of 16.3 inches. And we want to find the probability of getting a pizza that is less than 16 inches, which looks like this. Now our first step for these problems is always going to be standardize our distribution. Using our z-score equation and plugging in our data point of 16, we get 16 minus 16.3 divided by 0.2, or negative 0.3 over 0.2, which gives us a z-score of negative 1.5. So instead of finding the probability of a pizza x being less than 16 inches, we are now finding the probability of a pizza having a z-score less than negative 1.5. Now that we have a z-score, we can use our z-chart to find its associated probability. Looking at row negative 1.5 and column 0.00, we find a probability of 0.0668. Since we want to find the probability of being less than our z-score, and that being exactly what the chart gives us, we're done. We have a 6.68% chance of getting a free pizza. Next, we want to find the probability of a pizza being negative 1.5 Okay, first, let's draw our normal distribution centered at the mean of 16.3 inches. And we want to find the probability of getting a pizza that is less than 16 inches, which looks like this. Now our first step for these problems is always going to be standardize our distribution. Using our z-score equation and plugging in our data point of 16, we get 16 minus 16.3 divided by 0.2, or negative 0.3 over 0.2, which gives us a z-score of negative 1.5. So instead of finding the probability of a pizza x being less than 16 inches, we are now finding the probability of a pizza having a z-score less than negative 1.5. Now that we have a z-score, we can use our z-chart to find its associated probability. Looking at row negative 1.5 and column 0.00, we find a probability of 0.0668. Since we want to find the probability of being less than our z-score, and that being exactly what the chart gives us, we're done. We have a 6.68% chance of getting a free pizza. Next, we want to find the probability of a pizza being over 16.5 inches. Like before, our first step is to find this data point's z-score, which equals 16.5 minus 16.3 divided by 0.2, or 0.2 over 0.2, or just 1. So this time, we want to find the probability of having a z-score higher than 1. Looking at our chart for our z-score, we go to row 1.0 and column 0.00 to get a probability of 0.8413. But keep in mind, this chart always gives you the probability to the left of your z-score. Since the area under the entire distribution is always equal to 1, and the area by 1 larger than 16.5 inches. Not too shabby. Finally, we want to find the probability of getting a pizza between 15.95 and 16.63 inches. First, As always, let's find some z-scores. For 15.95, we get negative 0.35 divided by 0.2, or negative 1.75. And for 16.63, we get 0.33 divided by 0.2, or 1.65. Alright, we have our z-scores now, but how do we use them to find the area between them? Well, one way to do it would be first look in the chart for the larger z-score. This would get you this area here, to the left of 1.65. Then you can find the area to the left of the smaller z-score, which would get you this area in the tail here. Once you have those, you can subtract the smaller area from the larger area to leave you with the area in between them. Looking in our positive z-score chart, we find the area below a z-score of 1.65 is 0.9505. And then looking in our negative z-score chart, we find the area below a z-score of negative 1.75 is 0.0401. Subtracting these values, we get our answer of 0.9104, or a 91.04% chance of getting a pizza between 15.95 and 16.63 inches. Nope.
Cool, makes sense. Okay. Find the z-score, right? How do I let's write it on iPad, I think. Yeah, iPad seems fine. FC Barcelona. Tomorrow is Monday. Okay. Lesson 4. So we have z-score. So many ants here. Okay. And then the mean is convert this to z-score. Actually, this color is so nice. 0.1. It's around like 0.52. Okay, so it's roughly around 5.2%. Find the area. Okay, so he's saying that find the area 0.1. What? Okay. 0.47. 47 is 0.47 is 6.680. Yep, on the left, cool. And if you want on the right, you mine, okay, 0.8. 1.9.6 and you minus 1 to get left, yeah. If you on both sides, you find the left first, okay. 0.7, okay. Find 0.71, okay. And you find 0.28, 0.28, yeah. And then you minus together. Yeah. Lady boy. Lady boy. What is preference? Hide. Cool. Nice. Central limit theorem. Central limit theorem. Central limit theorem.
You should be familiar, even if you're not normal. The average is normal.
What?
Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about the central limit theorem, and it's going to be clearly explained. Note, for this StatQuest to make any sense at all, you should be familiar with the normal distribution. If not, check out the normal distribution, clearly explained. It would also be helpful if you were familiar with the concept of sampling from a statistical distribution. If not, check out Sampling from a Statistical Distribution, clearly explained. The central limit theorem is the basis for a lot of statistics, and the good news is that it's a pretty simple concept. In this StatQuest, I'll explain what the central limit theorem is and why it's important. Like most things in statistics, I think the central limit theorem is easiest to understand if we look at some examples. So let's start with a uniform distribution. This one goes from 0 to 1. It's called the uniform distribution because there is an equal probability of selecting values between 0 and 1. The probabilities are all equal and thus are uniform. We can collect 20 random samples from this uniform distribution and then calculate the mean of the samples. And on the right, we can draw a histogram of the mean value.
What?
Since we should be familiar with the normal distribution. If not, check out the normal distribution, clearly explained. It would also be helpful if you were familiar with the concept of sampling from a statistical distribution. If not, check out Sampling from a Statistical Distribution, Clearly Explained. The central limit theorem is the basis for a lot of statistics, and the good news is that it's a pretty simple concept. In this StatQuest, I'll explain what the central limit theorem is and why it's important. Like most things in statistics, I think the central limit theorem is easiest to understand if we look at some examples. So let's start with a uniform distribution. This one goes from 0 to 1. It's called the uniform distribution because there is an equal probability of selecting values between 0 and 1. The probabilities are all equal, and thus are uniform. We can collect 20 random samples from this uniform distribution, and then calculate the mean of the samples. And on the right, we can draw a histogram of the mean value. Since we only have one mean value, the histogram isn't very interesting. But after we collect 10 more samples and collect 10 more means, the histogram starts to look a little more interesting. Here's the histogram after collecting 20 samples and calculating 20 means. 30 means, 40 means, 50 means, 60 means, 70 means, 80 means, 90 means, and 100 means. After adding 100 means to the histogram, it's pretty easy to see that these means are normally distributed. However, to make it easy to see that the means are normally distributed, we can overlay a normal distribution. You might have noticed that in the last two slides, I put means are normally distributed in bold. I did this because this is what the central limit theorem is all about. Even though these means were calculated using data from a uniform distribution, the means themselves are not uniformly distributed. Instead, the means are normally distributed. Bam! Here's another example. This time, we'll start with an exponential distribution. Just like before, we can collect 20 random samples from this exponential distribution. And just like before, we can calculate the mean of the 20 samples. And lastly, we can draw a histogram of that mean over here on the right. After we collect 10 samples and calculate 10 means, the histogram starts to look a little more interesting. Here's the histogram after 20 means, 30 means, 40 means, 50 means, 60 means, 70 means, 80 means, 90 means, and 100 means. After adding 100 means to the histogram, we can...
What happened to this chair? Okay. Alright, it's good enough. Squish, squish.
And see that they are normally distributed. Even though these means were calculated using data from an exponential distribution, the means themselves are not exponentially distributed. Instead, the means are normally distributed. Bam! So far, we have seen that the means calculated from samples taken from a uniform distribution are normally distributed, and means calculated from samples taken from an exponential distribution are also normally distributed. Well, it turns out that it doesn't matter what distribution you start with. If you collect samples from those distributions, The means will be normally distributed. Yes, there's a little asterisk here that means there's some fine print that will come later. For now, just know it's really fine print and not worth spending too much time worrying about.
Oh my god, I'm sick, I think.
Double bam! Cool, but what are the practical implications of knowing that the means are normally distributed? When we do an experiment, we don't always know what distribution our data comes from. To this, the central limit theorem says, who cares? The sample means will be normally distributed. Because we know that the sample means are normally distributed, we don't need to worry too much about the distribution that the samples came from. We can use the means normal distribution to make confidence intervals, do t-tests where we ask if there's a difference between the means from 2 samples, and ANOVA, where we ask if there is a difference among the means from 3 or more samples, and pretty much any statistical test that uses the sample mean. Triple bam! Note, out there in the wild, some folks say that in order for the central limit theorem to be true, the sample size must be at least 30. This is just a rule of thumb and generally considered safe. However, as you can see in the examples here where I use a sample size of 20, the rule was meant to be broken. Here's the fine print. In order for the central limit theorem to work at all, you have to be able to calculate a mean from your sample. Off the top of my head, I can think of only one distribution, the Cauchy distribution, that doesn't have a sample mean. And after doing biostatistics for 20 years, I've never come across it in practice. That said, if you know of distributions that don't have means, put them in the comments below and tell us what they're used for. I'm curious about how common this occurs. Hooray! We've made it to the end of another exciting stat quest. If you like this stat quest and want to see more of them, please subscribe. And if you
If you're not normal, the mean is normal. Point estimate. Okay. Interval estimate. La, 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 la. Oh no. Oh, I see. Chest too squashy. No way. trust. What? Oh, 5%, yeah. 1%. Yeah. 10, 5, 10, 1. Yeah. Oops. Yep, then like this. Yeah. There you go. Okay. Now I'm comfortable. Yay. Look at the webcam. Mic. Hello. Alright. Confidence interval. iPad.
In this video, we're going to talk about how to find a confidence interval for a population mean, and also how to easily find a z-score that will help you to get the confidence interval, and also determining the value of the margin of error, also known as the error bound for the mean. So we're going to work on 2 example problems to illustrate how to do this. Number 1, the average test scores in a physics class is normally distributed with a standard deviation of 5.4. 50 scores with a sample mean of 79 were selected at random. Part A, find a 95% confidence interval for the population mean test score. Go ahead and try this problem if you already know what to do.
This is the formula. You plug it in and it works.
So we're dealing with a normal distribution. And that normal distribution has a population mean. We don't know what the mean is. However, we can estimate the population mean by means of a confidence interval. We know the standard deviation of the population, that's 5.4. The sample size is 50. 50 of a confidence interval. We know the standard deviation of the population, that's 5.4. The sample size is 50. 50 scores were selected at random. And the sample mean, x bar, is 79. So with this information, how can we construct a 95% confidence interval? The population mean, mu, is going to be between x bar minus z alpha times sigma over the square root of n. And its upper bound is going to be x bar plus z alpha times the population standard deviation divided by the square root of n. The confidence interval is going to range between the lower value, or the lowest value is going to be x bar minus the EBM, the error bound for the mean, and the highest value is x bar plus EBM. So notice that these two are the same. So therefore, the EBM is what you see here. The error bound for the mean is z alpha times sigma over the square root of n. So when writing the confidence interval, it's going to range between x bar plus or minus z alpha times sigma over the square root of n. Now the first thing we need to do is determine z alpha. Z alpha is going to be somewhere to the right of the mean. And the area that corresponds to z alpha is going to be the area to the left of z alpha. So the area of the shaded region highlighted in blue. Now there's a formula that can help you to calculate that area to the left. And here it is. The area to the left is going to be the confidence level expressed in decimal form plus 1 divided by 2. So the confidence level is 95%. So that's 0.95 as a decimal. So this is going to be 1.95 divided by 2. And so you should get 0.975 for the area. So that's the area of the shaded region.
What?
And here it is. The area to the left is going to be the confidence level expressed in decimal form plus 1 divided by 2. So the confidence level is 95%. So that's 0.95 as a decimal. So this is going to be 1.95 divided by 2. And so you should get 0.975 for the area. So that's the area of the shaded region. It's 0.975. Now what you need to do is you need to take the positive z-score table and get the z value that corresponds to this area. Now there's a lot of different z-score tables out there, but you want to use the one where it gives you the area from the left, not the area from the right. So keep that in mind. So using the appropriate z-score table, if you search for the area of 0.975, you should get a z-score of 1.96. So once you have that, you can now plug it into this expression. The next thing we need to calculate is the standard deviation of the sample mean, which is going to be the standard deviation of the population divided by the square root of n. So the standard deviation of the population is 5.4. The sample size is 50. So that's going to be 5.4 divided by the square root of 50, and you should get 0.76368 if you round it. So our 95% confidence interval is going to range from, let's see, x bar is 79, and then it's going to be plus or minus z alpha, which is 1.96, times the standard error, 368. That's 1.4968. To be in this 95% confidence interval is going to be 79 minus 1.4968. So that's 77.5032. And the highest is going to be 79 plus 1.4968. And so that's going to be 80.4968. So this right here is our answer for part A. So that is the 95% confidence interval. We could say that we're 95% confident that the mean for the population, or the mean of the average test scores in this physics class, is between 77.5032 and 80.4968. So if we were to take 100 samples, about 95 samples, or at least we expect that 95 samples will have a mean between these two values. The other 5 samples will have a mean outside of those values. So that's the basic idea behind the confidence interval.
Say that again.
Is between 77.5032 and 80.4968. So if we were to take 100 samples, about 95 samples, or at least we expect that 95 samples will have a mean between these two values. The other 5 samples will have a mean outside of those values. So that's the basic idea behind the confidence interval. So we're 95% confident that the mean is going to be between these two numbers. Now, what about part B? What is the value of the margin of error? The margin of error, also known as the error bound square root of the sample size. 100 scores with a sample mean of 82 were selected at random. Find a 90% confidence interval for the population mean exam score. Go ahead and try it. So let's write down what we know. The standard deviation is 6.
I think I'm sick. God damn it.
The sample size is 100. 100 scores were selected at random.
Okay.
And to estimate the population mean using a confidence threshold. So it's going to be the confidence. This is 9. 9 to it is the z-score distant from point up. So that's a quick 0.6. What's going to 0.0 is our 90% average test score in the chemistry class. Sample 5 times 6.5 over the square root of 100, and it's going to be 2 examples, and clearly illustrates how you can do that. What would you say? The confidence interval is the range of values that we expect the population mean to be located in with a certain probability. So as we said before, the confidence interval, it varies between a minimum value and a maximum value in which we expect the mean to be located in. It's the sample mean minus the margin of error to the sample mean plus the margin of error. So that is the confidence interval. The confidence level is the area under the curve in which we expect the population mean to be located in. So in the last example, we saw that the confidence interval, it varied from approximately 77.93 to 80.069. That's the confidence interval. It's a range of values. The confidence level gives us the area under the curve. So for a 90% confidence interval, the confidence level, my L looks terrible. The confidence level is 0.90. So that will be the area under the curve in which these range of values will exist in a normal distribution. Now, the confidence level is equal to 1 minus alpha. Alpha is the probability that the mean is outside of the confidence interval. So if the confidence level is 90% or 0.9, alpha is the 10% or 0.10. So let's illustrate this with a picture. So let's draw our normal distribution curve. So here is the population mean. Let's say this is positive Z alpha. We're going to say this is negative Z alpha. So the area under the curve of the region shaded in blue, that's going to be our confidence level. So that area is 0.90. So the 90% confidence interval is going to range between these two values. So our minimum value will be x bar minus EBM, and our maximum value will be x bar plus EBM. Now outside of that, we have the area shaded in red. So we said that alpha is 10%. So to the right, this is going to be alpha over 2. That's going to be 5%. And to the left, that's also alpha divided by 2. That's also 5%. So alpha is the area under the curve outside of the confidence interval, whereas the confidence level is the area under the curve within the confidence interval. Now let's talk about the effect that the confidence interval and the sample size have on the margin of error. So here's a question for you. If we increase the confidence interval, will the margin of error increase or decrease? What would you say? So let's say this is the length of a 90% confidence interval. The margin of error is going to be half of the length of the confidence interval. So that's going to be our EBM value. Now, let's say if we increase the confidence interval from a level of 90% to a level of 95%. A 95% confidence interval will be longer than a 90% confidence interval. So because the EBM is half of that, the EBM is going to be longer as well. So as you increase the length of the confidence interval, the margin of error increases as well, because they're directly related. The EBM is half of the confidence interval. Now what about if we increase the sample size? What effect will that have on the margin of error? Now keep in mind, the margin of error, the EBM, or the error bound for the mean, that's Z alpha times sigma over the square root of n. Notice that n is at the bottom of the fraction. Whenever you increase the denominator of a fraction, the value of the entire fraction goes down. It's an inverse relationship. Therefore, as you increase the sample size, the margin of error decreases. So there's two ways in which we can decrease the margin of error. The first way is to decrease the length of the confidence interval. If we decrease that, the margin of error will go down. The second option is to increase the sample size. Those are two simple ways in which we could decrease the margin of error. So that's it for this video. Hopefully it gave you a good introduction into confidence intervals and identifying the value of the margin of error. Thanks again for watching, and if you like it, don't forget to subscribe.
Cool. Exercise number 1. Okay. 2 point something. Okay, standard deviation. Oh no, it's a plus minus, sorry. Believe me if you know. It's normal. Yay.
The Z take 100 try scores.
Hello? 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 Right. even if you're not normal.
In a chemistry class is normally distributed